Let's start electrical machines with a review of some basic concepts from electromagnetic field theory. Okay, so very first concept is the Ampere's law. What is the mathematical form for Ampere's law? The line integral, closed line integral of the magnetic field intensity. This is equal to the total current enclosed, okay, along that path of integration. Okay, so if there is number of conductors here, okay, they are carrying different currents. Now if you are doing the line integration along this path, okay, now h bar will be tangential to this path, and if you integrate h bar dot dl bar, then this will be equal to the total current enclosed. And what will be the direction here? If you take the direction of the path of integration like this, then the current which is going in the upward direction, that is taken as positive. So if you have here, this is I1, this is I2 and this is I3. Here what is I enclosed? This is equal to I1 minus I2 plus I3. That is because this path of integration, if you see from the top, it is in the clockwise direction. Okay, so you have to basically follow the same principle of the right hand rule. Okay, so what does it state? Whenever you wound your fingers, when you curl your fingers around the conductor with the thumb in the direction of the current, okay, then the direction in which your fingers will curl around the wire, that is the direction of the magnetic field. Now let us consider a magnetic core like this, okay, magnetic material, and a wire, a conducting wire is wound over one of its arm in this manner. Okay, so using the Ampere's law, we will try to get some relations here. If current I is flowing in this direction, right, in this direction, then what will be the direction of the magnetic flux? Most of the flux will be confined to the core, right, because the permeability of the magnetic material is going to be very high. So most of the flux will be confined to the core itself. There will be some leakage flux. We will talk about leakage flux later. But right now we will assume that all of the flux is flowing inside the magnetic core only. So what will be the direction here? You can, in a similar manner, for each turn, you can wound your fingers and you can see that the effective direction will be in the upward direction. Okay, and whenever there is a coil, the easier way to see the direction of flux is just wound your fingers in the direction of this lines. Okay, so if you are wounding, then what is the direction of your thumb? It will be in the upward direction, right? So this will be the direction of flux phi. Okay, so now here we will try to apply the Ampere's law. Okay, if you take the path of integration as this path, okay, this closed path, then what will be the enclosed current? This will be equal to the current in each turn, right? This is I plus this I plus this I plus this I, right? So it will be the number of turns into the current. Okay, so if there are n number of turns, let us say n number of turns, okay, then the enclosed current is going to be n times I. That is the right hand side. Now we will consider the left hand side. So the path of integration is this, right? Now the magnetic field intensity all through this we will assume as constant. Okay, so h you can take out of integration, so you will be left out with what? H, if you take out of integration, you will be left out with integral dl, right? And so this will be integral dl is nothing but the whole length of this core. Okay, so that length of the core we will take as LC. It is called as the mean path length. Okay, so h into LC, where LC is mean path length. Okay, so this is the LHS. So from Ampere's law, HLC is equal to NI. So this implies that the magnetic field intensity, the magnitude of magnetic field intensity is NI by LC. Okay, so this is one important relation. Next we will discuss the magnetic circuits. What we do here, we create an analogy with the electric circuit, okay, and we try to analyze the magnetic system. Okay, so here we have a magnetic core on which a wire is wound, and the wire is carrying how much current? It is carrying current I. Okay. So a flux phi is produced. Now here the MMF, if you take the electric circuit, what will be the electric circuit? There will be an EMF source, electromotive force, and if you consider a resistance, it is connected to a resistance of value R, and here the current I will flow. So what is this equation? Ohm's law, we can write EMF is equal to I into R, right? Now here what is the analogy? EMF in electric circuits is equal to the MMF, the magnetomotive force in magnetic circuits, and the current in electric circuit is equal to the flux phi. Okay. And finally resistance, the analogous quantity here is the reluctance. Okay. So now what are these values? So the magnetomotive force, this is represented by capital F, and this is equal to N times I. Okay. So because there is a coil here, that the coil is producing the flux, so this we will consider as the magnetomotive force. Okay. If the current is high, the flux is going to increase. If the number of turns are high, then also flux is going to increase. Okay. So that's why MMF is equal to N times I. Okay. Now what will be the reluctance here? This you can actually derive, but we are not going into the derivation. I will directly write the expression. R is equal to LC by mu times A. What is LC here? This is the mean path length, and area, this is A is the area of cross section of core. So the more accurate way is actually the area of cross section through which the flux is flowing, the flux path, right? Now this is the flux path. So if the flux is flowing in this direction, what will be the area of cross section perpendicular to it? Okay. So that is the area of cross section of the core. Okay. So you can write the other also, area of cross section of the magnetic flux path. Okay, this is more appropriate. And mu is what? It is the permeability. This is equal to mu naught into mu r. Mu naught is the permeability of free space, 4 pi into 10 to the power minus 7, and mu r is the relative permeability of the material. So what is the final equation here? MMF is equal to flux times into the reluctance. Okay, and MMF is given by Ni, flux anyways it is as it is, and the reluctance is given by Lc by mu A. Okay, so this is the equation that we are going to use in the magnetic circuits. One more quantity here is the permeance. So this is nothing but the inverse of the reluctance. Okay. So what will be the analogous quantity in the electric circuits? It is the conductance. So permeance is, it is analogous to the conductance in electric circuits. Now the case of series and parallel combination. So just like resistances, when resistances they are having the same current flowing through them, then the resistances they are said to be in what? Series. Okay, and when the resistances are in series, we simply add them. Okay, similarly when the magnetic cores they are in series, different cores they are in series. Okay, then the effective reluctance is just going to be the addition. Okay, so series reluctance is given by R equivalent is equal to R1 plus R2 plus R3 plus so on till Rn. Okay, considering n number of reluctances are in series. Now what about parallel reluctances? It is also going to be similar to the expression of resistances in parallel, right? So 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus so on till 1 by Rn. Now even though magnetic circuits are very advantageous whenever we analyze the electrical machines, they have certain limitations. So we will see what are those limitations. Okay, so the very first one is leakage flux. So like I mentioned before only, whenever you consider a magnetic core and a wire is wound like this, what is going to happen? There will be magnetic flux that is produced. Say the current is flowing in this direction. Okay. So what will be the magnetic flux direction? This is going to be in the clockwise direction. Now most of the flux will pass through the magnetic core itself. Okay. Because the magnetic core, because of the high permeability, it will act like a low impedance path for the flux, right? But will all of the flux pass through the low impedance path, right? It will not, because if you consider, just like in the case of resistances, let us say this is about 1 kilo ohms, okay, and this is about 10 ohms. Now what will happen? Most of the current will flow in the 10 ohms because it is having a low resistance path. But 1 kilo ohm, the current will not be zero. Some amount of current will be flowing. Similarly, what will happen here is there will be some amount of flux that is leaking out of the magnetic core. Okay, and because it is outside the magnetic core, we call it as the leakage flux. It will not be useful flux. Okay, so when we discuss machines, it will become more clear to you. So you can write here, the magnetic core provides a low reluctance path. Okay, here in magnetic circuits we use reluctance, right? Provide a low reluctance path for the flux, but a small amount of flux is set up in the air, and this small amount of flux is called as the leakage flux. The next point is, next limitation is the non-linear BH curve. So we will discuss about this more, but we know that B is equal to mu times H, and H for a particular material should be constant. If it is constant, it means that B is proportional to H. There is a linear relationship. Okay, but if mu is not constant, then what is going to happen? You get a non-linear relationship, right? So that is the non-linear BH curve. And the third point is the fringing effect. So this occurs whenever there is an air gap, okay, in the path of the flux. So that means we took the magnetic core like this, right, previously. Now what we will do, we will have a small air gap here, okay, and if there was no air gap, how the flux lines would have been? It would have been parallel lines like this, okay. But now that there is an air gap, what is going to happen? The flux lines will travel at the edge like this, okay. So now what is happening? The area of cross section that is available for the flux, that is going to be larger when there is an air gap, okay. So that is termed as the fringing effect. So the area of cross section of the flux path will be larger at the air gap, right. And next we will discuss the magnetization curve in detail, okay, because this is a pretty important point. So if you draw the H, that is the magnetic field intensity on one side, and the magnetic field density on the other side. So instead of the magnetic field density, sometimes you will find phi also, flux, okay, and in place of H there will also be MMF, okay. So flux versus MMF curve will also be similar to the BH curve, okay, because these both are proportional and H and MMF are also proportional, okay. Now what is the expression that we already know? B is equal to mu H, okay. So now if you draw this BH curve, okay, B is y here and H is x axis, so mu should be what? It is nothing but the slope, okay. So for till a certain value, the slope will be constant. That means the permeability is going to be almost constant, okay. Now after a certain point, what is going to happen? So at that certain point, we call it as the knee point, the curve starts becoming non-linear, okay. That means the slope is changing, that is the permeability is now a variable quantity. So this is happening because of something called as saturation. So in a magnetic material, you're going to have magnetic dipoles, right? Now these magnetic dipoles, they align themselves in the direction of external magnetic field, okay? But what will happen when all of the magnetic dipoles have already aligned themselves? The magnetic field density will now remain almost constant even though you are increasing the MMF, okay? So that is called as the saturation. From beyond the knee point, it is called as the saturated region because there are no more dipoles left, or the dipoles that are left to be aligned, they are decreasing very rapidly, and finally, and before the knee point, you have the unsaturated region. So this is the limitation that we discussed previously, right? The non-linear nature of the BH curve. Now another important characteristic here is the hysteresis loop. So we will see what is this hysteresis loop now. So now we saw the BH curve, it was something like this, okay? Now what is going to happen when you are going to reduce, this is the path taken when the MMF is increased. Now let's say you are reducing the MMF, okay? So ideally what has to happen, the operating characteristics, they should come back all along the same line, okay? But what is going to happen, some of the magnetic dipoles, they are not going to go back to their original state even after the MMF is removed, okay? So that means even if MMF becomes 0, okay, there will be some amount of residual flux that is left out, okay? So if you decrease the MMF, this is how it is going to come back, okay? So first, if you are increasing, it will go in this direction. You can draw the arrow here, and when you are decreasing the MMF, it will come back in this path, okay? So what is this value here? Even when MMF is becoming 0, there is a non-zero value of flux, that is the residual flux. Now when will the flux become 0? It will become 0 when we apply MMF in the opposite direction, okay? That means negative MMF, okay? Here it is becoming 0 at this point, okay? So if MMF is reduced to 0, there will be a non-zero value of flux, and if you are further reducing the MMF towards the negative values, then the flux will become 0, okay? So in the opposite side, you are now increasing the magnitude, right? So in that direction, you will get a similar curve. So here also, to a certain extent, the curve will be linear and then it will become saturated, okay? Now here it is increased, okay? Now again you are further reducing the magnitude. That means we are reducing the MMF in this direction, okay? So now what is going to happen? The curve, it is going to come like this, okay? So now you have changed the value from negative value to 0 MMF, and here also again, once again, there will be some residual negative flux, okay? And finally, if you are further increasing, then it will go back to this point, okay? So this is how the curve is going to be, the actual curve. In the first time only, when you are applying the MMF, it will follow this middle path, right? After that, when you are reducing the MMF to 0, there will be a residual flux. So you can write here, this is the residual flux, okay? And then you are applying the MMF in the negative direction, in the opposite direction, okay? So here in the opposite direction, the magnitude is increasing. So the same curve will be there, okay? The flux will now increase in the negative direction, okay? And the flux, the point at which the flux becomes 0, this is called as the coercive magnetic field, okay? And here also it will reach a saturation point. Now once again, in the opposite direction, whatever flux was there, that magnitude you are decreasing, okay? So MMF is going towards the origin, right? Now here at this point, MMF has become 0, but there is still some flux. This is the residual flux in the opposite direction, okay? So once again, you have to apply the MMF in the opposite direction. So negative flux will become 0 and then it starts increasing towards the positive value, Okay. So the BH operating curve for varying MMF, for alternating MMF especially, the operating point is going to rotate about this loop. Now we will discuss the core losses. So this is nothing but the losses which occur in the magnetic core. Okay. So first one is the hysteresis loss. So we already saw that the BH curve, it is non-linear, and the losses, why will the loss occur, is because of the different characteristics when the MMF is increasing and decreasing, right? So when it is increasing, it is going to be something like this. When it is decreasing, it will come back like this. Okay. And similarly, the opposite direction, it is going to be like this. Okay. So now what is happening, in order to make the residual flux 0, extra energy is being used, right? Extra MMF has to be supplied. Then only the flux will go back to 0. Okay. Now where will this extra energy come from, right? That will be accounted as the hysteresis loss. In the electrical machines, this is derived from the input power. Okay. So that is one kind of core loss that we see. So you can see that it will occur at every cycle, right? Now the area of this loop, it will give a measure of how much is the hysteresis losses. So if the BH area is small, that is the hysteresis loop itself is small, then the hysteresis losses will be small. If the magnetic core has a larger hysteresis loop, that means the area is large. In that case, the losses will also be large. Okay. So this is the hysteresis, area of hysteresis loop is a measure of hysteresis loss. Okay. Now the next loss is the eddy current loss. Now what happens here is, if you consider the magnetic core, a wire will be wound over it. Okay. Now let's say the wire is carrying an alternating current. When the current is alternating in nature, then the flux is also time varying, right? Alternating current gives an alternating flux. So alternating is nothing but time varying, right? It is changing with respect to time. So when there is a time varying flux, an induced EMF will be produced, right? So an induced EMF will be produced in the magnetic core. Okay. So you can write this alternating flux, which is time varying, is going to induce voltage in the magnetic core. So once voltage is induced, what is going to happen? The electrons that are present in the magnetic core, they are going to experience a force and they are going to move within the magnetic core, causing the electrons in the magnetic core to move. Now when electrons are moving, what does it mean? It is nothing but current, right? So this movement of electrons in the magnetic core is termed as the eddy current. Okay. The movement, this movement of electrons in magnetic core is called eddy current. Now when there is a current, okay, the magnetic core is resistive in nature. So when there is a current and when there is a resistance associated, then there will be losses in the form of heat. Okay, and that losses is called as the eddy current loss. So you can write, since the core is resistive, eddy currents lead to a loss in the form of heat. Okay. So this is called as the eddy current losses. Now one very popular way in which these eddy currents are reduced, that is by the use of laminations. Okay. Laminations are used to reduce the eddy current losses. So what are these, what is meant by these laminations, right? So let us say this is the one side of the magnetic core. Okay. So this is what a bulk core, that means the entire material is one and the same. Now in laminations what is going to happen, there are going to be numerous cores which are separated by some insulating material, usually it is some kind of resin. Okay. So in this way the laminations are very thin, so they are going to restrict the path of the electrons. Okay. And since they are all insulated from each other, all these different laminations, there will not be any current between these laminations. Okay. So laminations are separated by insulating material. So this is one point, and the other point is the thin laminations restrict the path of the eddy currents. So these are the two kind of losses that occur in the magnetic core.